All right. This is banking the curve problems, or sometimes you hear them called negotiating the curve. So I made a little joke here, like, students, they negotiate the curve all the time, right? Okay. This first example is very similar to the advanced circular motion lab that you did, on in class the first day we came back from the semester. Or from the break. But we have here, this is a puck of mass m is attached to a string that passes through a hole in the table. So there's a hanging mass right here. The puck is actually set to move in a circle at a certain speed, and if it moves fast enough, it actually keeps this mass down here at rest. Okay, so if I start analyzing the forces here, I've got on the lower mass, I've got tension going up, and then I've got capital MG going down. Okay, and then up here, I've got the tension force, which should be the same thing. Okay, shouldn't be any friction because it says the table is completely frictionless. Also, there's no friction on the puck. Okay, and what I can say for the block, okay, this is big M. Okay, for the block, what I'm going to say is that the tension force has to be equal to mg to keep the block at rest, right? If it's unbalanced, then it's going to move and it's not going to be at rest anymore. Well, that means that this tension force has to be the same as the one on the puck. So for the puck, okay, what I'm going to say instead of saying just this, because we know this is true, I'm instead going to use that this string right here, the tension is actually providing the circular motion to the puck. The puck is going to move in a circle, okay, but this is the centripetal force that's causing it to move in a circle. So the tension force acting on the puck is actually going to be equal to mv squared over r, okay, or m times a sub c. This is just the centripetal force equation, okay? And I mean, if I did m a sub c, right, a sub c is just v squared over r, so it doesn't really matter, okay? Okay, so here's what I'm going to do. I'm then going to, I then should understand, right? Okay, wait, if tension force is equal to capital Mg and tension force is equal to mv squared over r, little m v squared over r, then wait a minute, I should be able to set those two equal to each other. And guess what? I can. So mg equals little m v squared over r. Okay. Okay. And when I do that, okay, let's see. These two m's can't cancel out because they're not the same. Okay. But I can get v by itself. So if I multiply r on both sides and divide little m, I should end up getting v squared equals capital M G R, okay, over little m. Okay, and then I can root both sides and get my true equation for my velocity, which is root capital M GR over little m. Okay, so there's that. Okay, now I'm just going to plug in all my numbers. Okay, so V is equal to, or let me just draw an arrow there. V would be equal to root, what's big M? Big M is 20. Okay, 20, G is 10, R is 2, and then um, little m is going to be 4. Okay, so you calculate the whole thing out. Okay, 20 times 10 is 200 over, so 20 times 10 is 200 times 2 is 400 over 4 is going to be 100. Root of 100 is going to be 10. So I should get that velocity is equal to 10 meters per second. Okay, that's the minimum speed required. It'll keep the bottom mass at rest. Okay, which is good. Okay, roller coaster car example. We did a little bit of this with Hot Wheels cars last year. Okay. Um, First off, normal force on the car at the bottom of the loop. This is really important to understand that at the bottom of the loop, the normal force is not just going to be equal to mg. Okay, because uh, uh, the what would actually um, because the normal force would not just be equal to mg. The reason for that is because you have an acceleration going up, which means you have to have an unbalanced force going upwards. Okay, and that should make sense because why are we having acceleration going up? Well, it's because as the car is moving, the velocity is changing its direction so that it can go around the loop, right? So you notice it's going directly to the right, but then it goes in a loop, right? So the velocity is changing its direction as it loops around. Okay, and it doesn't lose or gain any mechanical energy, which is important to note. So we can do conservation of energy just fine. Okay, but to figure out the normal force, I can't just set it equal to mg. What I have to do is I have to find the net centripetal force, which would be normal force minus mg equals mv squared over r. Okay, and capital R, I'm just using that because the problem uses capital R. Okay, well, you can use either one, doesn't really matter. Okay. Okay. To get the normal force, I'm just going to get normal force by itself. That's going to give me mv squared over r plus mg. Okay. And if you really wanted to, which I kind of want to, I'm actually going to simplify this equation to be f sub n equals mv squared over r. Okay. You notice how I took the m out. Okay. Plus um, mg. Okay. Oh, not mg. Sorry. I had like an astounding realization. I have to go fix something after I finish with this. Okay. Um. Maybe maybe I already fixed it. I don't know. Okay. I'm sorry. I don't know why I'm thinking of it right now. Okay. And then I'm just gonna plug in all my values. So normal force is equal to the little m, which is 300. Okay. V is 40 squared. R is 30, and then G is 10. Okay, and if you plug all that stuff in, you could punch all that stuff into your calculator, and you should end up getting about 19,000 newtons, which, by the way, so to figure out, so that's your normal force, right? And the weight of the cart is about 3,000. So let's see, because it's 300 times 10, which would be 3,000. Okay, so 1,900 divided by 3,000, that's about 6.3 Gs. Now, that is a little, this is a different case because it is the bottom of a loop, okay? But that is a lot of Gs, by the way. So if you go over 5 Gs, that actually will break your bones. So this is kind of a really, really this is a really really sharp turn. It's crazy to think about. Um, okay, so then calculate the speed of the car at the top of the loop. So at the top of the loop, okay, I'll use pink for this. At the top of the loop, it's got again, normal force is now pointing down. Mg is still pointing down like always. Okay, now the other things that are here, we can use energy conservation. That's going to be the best way to do it. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Okay. Okay. And when we do that, well, we don't have any potential energy initially, so we can ignore that term. Okay. But we will have both at the end. So what I'm going to do is I'm going to do 1/2 mv initial squared equals 1/2 mv final squared plus mg y, my height. Okay. I'm not going to make any substitutions yet. Okay. Okay, really quickly, right off the bat, you should notice that you've got m's in everywhere, m's in everything, so you can cancel those out. Okay. Okay, so here's what I'm gonna do. I'm just gonna substitute everything in now. Okay. 1/2. Okay, so this is just 1/2 v. I'm not substituting everything in. I'm just rewriting it. Okay. V final squared plus gy. Now gy, this is gonna be g times 2 times the radius, because y is going to be 2 times the radius. Okay, so y would actually be 60 meters. Okay, because that's what it says right there. Okay. Okay, now I'm going to plug everything in. I don't know why it took so long to get to the plugging in stuff, but now we're getting there. Okay, the initial speed is 40. Okay, we don't know the final velocity yet. That's what we're trying to figure out. This is going to be 10, and this is going to be 60. Okay, what you should see in this first term, 1/2 40 squared, this ends up being 800. Okay, so this will be 800 equals 1/2 v final squared plus 600. Okay, and if you subtract the 600 from both sides, you get 200 equals 1 half v final squared, multiply by 2 to get 400 v final squared, and then you can take the square root to get 20. Okay? So that's the velocity at the top of the cart, at the top of the loop. Now that's not the whole problem because we actually do need to figure out what the normal force is at the top of the loop. Okay, I'm gonna do it in this little box right here. It's not gonna take very long. All I gotta do is just use that equation I derived earlier. Normal force is equal to mv squared over r plus g. Okay, and all I gotta do now is plug everything in. The mass is 300. Okay. The velocity, the final velocity is 20. So 20 squared over the radius, which is 30 plus 10. Okay. And when you plug all that stuff into your calculator, you should end up getting about 1,000 newtons. So the number of G's decreases considerably because now this is about a third of the mass, so you'd experience about 0.33 G's. So close to falling off the track, but not quite. Okay. Not quite. Okay. This is the normal force at the top of the track. Okay. Oh gosh, I just like absolutely threw my pen. You should have seen that. That was actually quite impressive how I like managed to throw it. Okay. The next example is okay. So this is mentioning something called a Lave cube. If you don't know what a Lave cube is, it's a cube upon which the face of Icelandic musician Levi is superimposed. If you actually Google Lave cube, you will find somebody made a template that you can print out and it's literally a cube, and every side is Levi's face, and you just fold it, and it's a cube, and it has Levi's face on all sides. It's pretty funny. Okay, I actually first found it on TikTok. Okay. So we have like suppose we have the cube at the top. It's released from a height h above the ground on a smooth frictionless track. It glides down, goes through the vertical loop. What's the minimum height I need to release the cube from? Well, to figure that out, I'm going to use a couple of important physics principles. The first thing is that if the normal force is equal to 0, the cube falls off. And Leve can never fall off, so we don't want that, okay? So what I'm going to do is when the cube is at the top, okay, it's going to have two forces, normal force and mg, okay? And those both together provide centripetal force. So what I'm going to do is I'm going to do normal force plus mg equals mv squared over r, okay? Is the radius, okay, radius is lowercase r in this problem, so I'm going to use lowercase r, okay? Okay, now what you should notice is that if f sub n is equal to 0, the cube falls off. Well, then that would actually give us our minimum speed. So I'm going to take my f sub n, and I'm going to get rid of it, because if this is equal to 0, then the cube would fall off. We're going to find the absolute minimum, right? I guess this wouldn't be the minimum. This would be like just when it falls, okay? Okay. Then you got mg equals mv squared over r. Wait, we got m's on both terms. Let's get rid of those, okay, because I don't care about them. So we've got g equals v squared over r, okay? And that is, you don't have to be a rocket scientist to figure that part out. All that's going to give you, if you derive this, you multiply by r on both sides and then root, you end up getting v equals root gr, okay? Okay, and we use that quite a bit in Physics 1. I think we did quite a few labs in where we used root GR, but you're going to use it the same thing here. Okay, now one thing that we can do, okay, is we can then use conservation of energy to solve the problem, okay? So I'm going to use conservation of energy, mg capital H equals 1 half mv squared, so it is going to be moving at the top. It'll have some velocity v, that's what we're going to call it, and then plus mg to r, because the radius, right, the height is this whole height right here, the whole diameter of the track, okay, not just the radius, the diameter is 2 times the radius, okay? Okay, I can make another substitution here. I can put v in for there, okay, which is what I actually need to do. But I also should also notice right off the bat that we've got m's in every term here. So this speed is actually irrespective of mass, which is pretty neat. So g capital H equals 1 half. Okay, now what I'm going to do for v, okay, is I am going to substitute the root gr. Hey, wait, root gr squared is just going to be gr. Let's do 2GR. Okay. Oh, wait a minute. G not is also in all my terms, so I can get rid of those. Okay. And this actually gives you straight up what you need because you were trying to get H, right? You're trying to get H from this, so it's just 1/2 R plus 2R. Or you can say that that's 2.5 R if you wanted to, or you could leave it like that. I don't really care. Okay, I mean, it all means the same thing. It's all going to work out. I mean, at the end of the day, right, the universe is still going to end. Okay. Okay. The Lord Ball. This does not exist. If you find, you may be able to find it online, but if you do find it, then I mean, let me know because I'm a huge fan of Lord. But the Lord Ball. Okay, it's a ball upon which you don't really need to know that for the problem. It's not critical to the problem. I just put it in there to be funny. Okay, I try to make things funny because physics C is torturous. Okay, but the ball has two forces acting on it. It's got mg going down, and then it has the tension force going diagonal here. Okay, the two components as well. Okay, there you go. And then your angle theta is right there. Okay, this part has to be ft cosine theta because it's touching the angle. This part has to be ft sine theta, okay, because it's opposite the angle. So what I'm going to do, right, is I can define the the forces in the y direction, okay? What I can do is I can say that ft sine theta needs to be equal to mg to keep the ball from falling. Okay, and we don't want the ball to fall any, we want it to stay at the same height. The x component forces are going to be ft cosine theta, and that's just going to provide my centripetal force. Okay, so that's going to give me mv squared over r. Okay, is R capital? Yep, R is capital in this case. So I'm going to use capital R just for consistency's sake. Okay. Okay. Now what I can do just by algebra, okay, is I can actually divide the two of these. And now let me tell you really quickly, when I'm dividing the two of these, this is actually a shortcut to what I would normally do is I would get f sub t by itself in one of these equations and then plug it into the other. This is a shortcut, is dividing the two. I have to divide the y by the x though, because otherwise I'm going to get something really wonky. Okay, um, so I will do ft sine theta over ft cosine theta and set that equal to mg over mv squared over r. Okay, and you're going to notice a lot of things happen here. Okay, your ft's are going to cancel out. Your sine over cosine is going to become tangent. Your m's are going to cancel out, and then your r is going to move up into the numerator. Right? That's just a lot of algebra stuff. Okay, I just kind of threw it all in there so that you can see what I'm doing. Okay, so I end up getting tangent of theta equals RG over V squared, right? There's a really good burger place in Denton called RG's Burgers, and I love that place so much. I haven't been in so long, but I want to go again, okay? But that's what I'm thinking of when I see this, okay? Okay. And then I'm just going to plug all my numbers in. I get tangent theta. You can do inverse tangent if you want, but I'm actually going to skip that part, and I'll show you why, because I'm smart like that, okay? Equals R is 30, okay? 30, G is 10, and then V squared is 20 squared. This ends up being 300 over 400, which ends up being 3/4. And if you know, so this ends up being tangent theta is equal to 3/4. What theta will make that true? And that's actually on the formula sheet, which I do not have a copy of with me right now, but that's actually on the formula sheet, okay? It would be 37 degrees, okay? Now, to figure out what the tension is, that's only half the question. We figured out the angle, but we need to figure out the tension, okay? To figure out the tension, okay, what you can do, there's two ways to do it. This is the longer way, is to do Ft would have to be equal to the Pythagorean theorem of the components. So Ft cosine theta squared plus Ft sine theta squared, okay? You could do that if you wanted to. That's a little bit much. But you were like, oh, but Mr. Mitchell, I don't know what FT is, right? So I can't actually solve it. Well, you know what they're equivalent to. So you could do, you know, mv squared over r squared plus mg squared. And maybe that's faster for you. Great. But this is, in my opinion, not the best way to do it. Here's actually the best way to do it. Take this expression up here at the top, ft sine theta equals mg, and then plug in everything. You know what theta is, you know what m is, you know what g is. Just plug in everything and get ft by itself. That's the easiest way to do it. So you would get ft sine theta. Sine of 37 is going to be 3/4, okay? Or sorry, 3/5. Sorry, it's 3/5. Okay, and then the mass is 3g is 10, and you end up getting 50 newtons. Okay, isn't that's so much faster than doing it the other way? So much faster. Okay, so don't do more work than you need to. Right? Okay, this is the banked curve problem. Okay, we call this, sometimes it's called negotiating the curve, sometimes called banking the curve problem. Okay, but banking the curve is basically, so here's kind of a fun fact, right? Did you know that if a track has no friction, if a road has no friction, you actually can get a car to complete the turn if the road is banked a certain amount? Okay, that's why if you've ever been to the race car tracks, the one I'm thinking of is Texas Motor Speedway. Texas Motor Speedway is like on the way to Fort Worth from Denton. I don't really know that because I used to live kind of close by there, but Texas Motor Speedway is down that way, and if you've ever been to any race car track or anything, you'll notice that the turns are banked pretty steeply, and that's because that's to assist the race cars as they go around the track, right? Because they're going so fast, they need to have a lot of banking to be able to take those turns at those speeds. Okay, so this is an example, and this is a really weird looking car. I'm thinking of like the Halo Combat Evolved Warthog, I guess. Okay, but there's a couple. The forces acting on the car. You have capital MG going down. You've got normal force pushing out onto the out of the track. Okay. The normal force has two components. It has a component that points in towards the center of the circle and a component that points upwards. Okay. And now here's the thing. I'm given this angle theta right here, but I don't know what angle would that be up here. It's actually going to be this top angle right here. Okay. Actually going to be that top angle right there. Okay. Huh, weird. So the opposite here is going to be Fn sine theta. This is going to be Fn cosine theta. Okay. So it's kind of weird, but it's kind of weird. Okay, but it is what it is. Okay. Okay. So if I define, okay, so this is my x direction, this is my y direction. If I take my x direction, okay, my x direction forces, that's going to be Fn sine theta. That's going to be equal to the centripetal force mv squared over r. Okay, is r capital in this case? Yep. Okay. What about the y direction forces? Well, the vertical needs to cancel out because it's not moving up or down, so it should be Fn cosine theta needs to be equal to capital Mg. Okay. I'm sorry, I kind of wrote over that. Okay. Okay. Take these two equations, divide by one another. Again, same thing as getting Fn by itself in one of the equations and plugging it back in. It's just a shortcut. Okay. So I'm going to do Fn sine theta over Fn cosine theta equals mv squared over r over capital Mg. Okay, they're both capital M's. I don't know why I keep saying capital M. Okay. Do you notice again your normal forces? Those cancel out. These turn into tangent. M's cancel out. R goes down to the bottom now. Okay. Do you notice all that stuff happening? Okay. So I'm just going to show you what this should end up giving you. It's going to be tangent theta equals v squared over gr. Okay. That's what you should end up getting when you've mathed that whole thing out. Okay. So to figure that out, I just need to get v by itself, which is really easy to do. I multiply gr on both sides, so I get v squared equals gr tangent theta. Okay. And then I root both sides. V equals GR tangent theta. Take the square root of both sides, okay? Or take the square root, okay? And then I just got to plug everything in. Okay, so I'm going to do that really quickly. Root, this is 10, R is 120, and then tangent theta, so theta is 37. And if you think back to the last problem we did, tangent of 37 degrees is going to be 3/4. Okay, and so when I multiply all this stuff together, okay, I should end up getting root 900, and root of 900 is going to be 30. Okay, so this is the exact speed that the car must travel to successfully navigate the curve without falling off if there's no friction on it. Okay, so the car needs to go 30 meters per second, and it will be able to complete the curve without having to worry about any friction or slipping off or anything like that. Okay, wow, that was a little bit more involved, but I think it was kind of fun. All right, gaslight, gatekeep, girl boss. Peace out, Girl Scout. Have fun.